Hello, this is the CUDAN Open Lab seminar on April 27, 2026.
27.
And today it is our greatest pleasure to have Carla Scaletti, who will speak on auditory analytics, sonification and analytical listening for exploration and discovery. And this is a rather special kind of thing because typically we are asking the community to sort of like suggest speakers, but I think I should share the anecdote how I found Carla. So since 10 years, I have a kind of like fascination for sonification and electronic music, which came out of a failed DARPA project. And this went a little bit out of hand. And I dove deep into the literature in this direction. And last year I was in Oxford, and they have a bookstore. As every good university city has, there's a flagship bookstore, which has a huge music section. And this music section sort of stops with Stockhausen and the Schoenberg, the usual suspects, all dudes, by the way. And I thought like there must be something more contemporary and there must be something more female. And so basically what happened is I ended up with a section that was like the half the size of a Billy shelf near the cashier. And there were like indeed 5 books about female musicians. And I took one of them home, which was called Pink Noises. And I took it home because there was an interview in there of Leandra Dieg and Pauline Oliveros and a bunch of other people I didn't know. And Carla Scaletti's interview is wedged right in between. And so once I've read the ones I knew, I thought like, maybe I should read that one next because, you know, you're not sort of like neutrally sandwiched between Eleanor Dick and Pauline Oliveros, I assume. And my mind was blown. So what we will hear in the next 50 minutes and basically hopefully discuss in the 2 hour slot is the perspective of a person who is a musician, but also an engineer, and also somebody who went very, very deep into complexity science and has an understanding which is really widening sort of like our own consciousness regarding how all these things play together. And I give you one concept which sort of triggered this invitation, which is Carla says in this interview that the human brain is like an infinite impulse response filter, meaning we have a very, very long delay, and then sort of like something happens when we say something. And that thing is super fascinating because today we deal with lots of devices that have an input and an output, and there's something going on in between, including machine learning and so on. And in cultural data analytics, we do this a lot. And so I thought like that would be really, really cool to hear from somebody who does this since the 1990s and not only does something which, you know, other people do too, meaning building instruments, but we're talking really profound instruments, like, for example, an APU, an audio processing unit, which does what the GPU does for graphics, but for sound. And so that is sort of very well known in computer music circles and used because Carla is the president of the Symbolic Sound Corporation that produces such devices. But I think it should be more widely used and may help us to get beyond this paradigm that we have in multidisciplinary science, that we take some data and then we sort of like pipe it through some IPython notebooks or whatever your scripts are. And in the end, we have a static paper with some static figures. That is all nice in academia, but that's not how the world works because in the world you have sort of like lots of inputs and outputs and devices and filters where something happens. So I'm super, super excited to looking forward to what Carla has to say. Carla, the stage is yours.
Thanks so much, Max. And thanks, Mikhail. And thanks to the whole Open Lab for this invitation. Um, and thanks for scheduling the lecture today, which is International Morse Code Day. Samuel Morse was an artist. This is a self-portrait of his. He came up with the idea for the telegraph during a long sea voyage back to America from Europe, where he'd been studying portraiture. Inspired by stories that he'd heard about parties where Benjamin Franklin would get all his guests to hold hands while one of them touched a Leyden jar, it seemed to Morse that electricity could travel through a circuit almost instantaneously. And he thought that if the presence of electricity could be made visible at some point in the circuit, it wouldn't be difficult to construct a system of signs by which intelligence could be instantaneously transmitted over long distances. But the system of signs he came up with was not what we call Morse code today. It was his collaborator, Alfred Vail, who came up with the idea of mapping each letter to a combination of long and short pulses separated by pauses, along with the clever twist of mapping the most frequently used letters in English to the shortest codes. Compare the length of the codes for E and T to the length of the codes for J, Q, and Y. In the Morse-Vail telegraph, when you press down a transmitter key, it completes a circuit. And at the receiving end, a stylus makes an indentation in a paper tape, which is advanced at a constant rate by a clockwork mechanism. To decipher the message, a receiving operator would read the indentations in the paper tape and write the corresponding letter below each group of dots and dashes. So Morse's original concept was literally writing at a distance, telegraph. But then something kind of unexpected happened. Telegraph operators all over the world started to recognize common letters or words by ear from the pattern of the clacking sounds made by the machine. Not only that, but they could do this so-called sound reading more quickly and more accurately than they could transcribe from the indentations left in the paper tape. With practice, the telegraphers got so skilled at sound reading, they could transcribe a message by ear and write it down on paper as it came in real time, often just discarding the paper tape at the end. By repeating a word, you can start to get a sense for how the operators began recognizing common words. So pretty quickly, you start to experience this transition from hearing a sound to hearing information. For the Paris Expo in 1855, Morse held a competition to find the fastest telegraphers, so he could show off his invention at the fair. The fastest and most accurate telegrapher was an operator from Kentucky named James Francis Leonard, who averaged 50 words a minute and had a peak rate of 55. And it turned out he relied exclusively on sound. That convinced Morse and Vail to replace the original paper tape telegraph with the telegraph sounder, a device designed specifically to make sound. It was an intentional shift from a visual to an auditory user interface, led this time by the users of the technology, because it gave them faster and more accurate results. As James Reed wrote at that time, the ear was found more reliable than the eye. In the 1870s, the constraint was one wire, one message, which is part of what led Alexander Graham Bell to the idea of the harmonic telegraph. In 1875, Bell wrote to his future father-in-law, Gardner Green Hubbard, proposing that he could send multiple messages along a single wire by using a different frequency for each sender-receiver pair. Because, as he wrote, just as any number of sounds can be transmitted through the same air without confusion, any number should be able to pass along the same wire. So the harmonic telegraph was an early example of frequency division multiplexing. In his 1876 patent, Improvement in Telegraphy, Bell describes how each bidirectional sender-receiver pair would share a common frequency determined by the resonant frequency of a tiny strip of metal. So in this diagram, the blue strips are one frequency, the green strips have a different resonant frequency, and the orange strips share yet a different frequency. So even when there are multiple senders and multiple receivers along the same line, each unit responds only to its own resonant frequency. Initially, Bell tried the traditional telegraph approach, a make and break circuit, pulsing at the resonant frequency. The problem is an instantaneous switch contains an infinite number of harmonics. So the different sender-receiver frequencies were overlapping and interfering with each other. Bell's breakthrough was to shift from discrete pulses to what he called undulatory current. Instead of abruptly switching the current on and off, he induced a continuous sine waves of current at each resonant frequency. Then the principle of superposition meant that he could now stack dozens of different frequencies on the same wire, and they would add without interfering with one another. Once he'd figured out how to transmit continuously varying sinusoids, Bell realized he could replace the tuned metal reeds with a metal plate that could vibrate at any frequency. And if you hooked up one end to a speaking tube and the other end to a hearing tube, you could transmit articulate speech across the telegraph wires. In other words, figure 7 of the harmonic telegraph patent is the telephone, presented almost as an afterthought. Bell was describing a kind of indexical mapping from the vibrations of a physical object to an air pressure wave, to vibrations in a membrane, to continuously variable current on a wire, and back again. Bell's favorite invention, the one he most wanted to be remembered for, was not the telephone, but the photophone. In the telephone, vibrations in the air are transduced to variations in electrical current. In the photophone, vibrations in the air are used to modulate light. For the photophone, Bell replaced the flexible membrane of the telephone with a flexible mirror that becomes alternately convex and concave as it vibrates. A beam of sunlight is directed at the vibrating mirror, and the reflected light is beamed to a remote receiver, a selenium cell, which transduces variations in brightness to variations in electrical current, and from there to variations in air pressure or sound. Bell used the photophone to transmit the world's first wireless voice message, using nothing but ordinary sunlight. In 1880, Bell wrote an enthusiastic letter to his father, speculating about future applications of the photophone, several of which seem to anticipate some modern-day applications of auditory analytics, like being able to identify stars by their characteristic sounds, or being able to study sunspots and storms by the noises produced by the photophone. In the course of experimenting with the photophone, Bell stumbled across a strange phenomenon. He noticed that thin disks of different substances would emit distinct sounds when exposed to a rapidly interrupted beam of sunlight, now known as the optoacoustic effect. This occurs when pulses of light cause heat expansion and contraction in matter and create a sound pressure wave. Bell reported his findings in Science in 1881 in a paper titled The Production of Sound by Radiant Energy. In that paper, Bell describes a new scientific instrument he invented called the spectrophone, which he made by literally replacing the eyepiece of a spectroscope with a hearing tube. Much like a visual spectrograph display, the sound of the auditory display depends on which bands of the electromagnetic spectrum are absorbed by the substance. So in 1881, Bell describes using the ear as a scientific instrument for exploration, investigation, and research. And like researchers using auditory analytics today, Bell advocated using sound as an adjunct to visual representations, and especially in situations where you can't use your eyes. For example, because we can't see infrared radiation. In his 2003 book, The Audible Past, Jonathan Stern describes this period in history as the age of ensoniment, a kind of auditory parallel to the Age of Enlightenment. It was a period of time when people began to develop listening as a rational skill in order to work with new technologies like the stethoscope and the telegraph. Stern calls this skill of rational listening audile technique. It's the idea that the human ear can function as a precise scientific tool capable of extracting information from a complex field of sound. Stern was not talking about the technology for making data audible. His focus is on the skill of listening as a directed, learned discipline and a skill that you can hone over time. Listening requires hearing, but it's not simply reducible to hearing. When you use audile technique to transcribe Morse code, you aren't just hearing sound, you're interpreting data. Audile technique associates listening with logic, analytic thought, professionalism, discipline, and mastery. And Stern's history offers a counter-narrative to the romantic notion that sight is a sense of the intellect and precision, while hearing is a sense of feeling and emotion. It's this 19th century skill of rational listening that forms the foundation for modern auditory analytics. By discovering that they could decipher the same message from the incidental clacks of the machine as they could from the visual marks intentionally inscribed on paper tape, 19th century telegraphers demonstrated an important idea: information can be independent of its physical manifestation. Likewise, Bell's insight that he could map vibrations in the air to fluctuations in electrical current or variations in light intensity and back again to sound showed that information can be decoupled from its realization. In the 19th century, when you built a machine to solve a specific problem, and then you wanted to solve a different problem, you had to physically change the machine. Like when Bell replaced the tuned reeds with a rectangular plate, and then replaced the rectangular plate with a flexible mirror. What's different now is that we've agreed on a kind of a universal substrate, a system of signs or symbols that, like Morse code, we've agreed to adopt in common. In our case, it happens to be a binary representation, but it didn't have to be that. It's this universal substrate that's made it possible for us to develop layers and layers and layers of software that function as a kind of universal virtual machine that we can manipulate symbolically. And because we share this common substrate, we suddenly find ourselves all playing in the same sandbox. Digital audio signals, historical cultural data, molecular dynamics simulations, epidemiological or climate models, all of them can be stored or generated as abstract, interconnected networks of structures and streams of numbers in the universal virtual machine. So it's only natural, or maybe inevitable, for some of this data, some of this information to cross over from one field to another. And from the universal substrate, we can map data, even totally imaginary data, to physical energy and matter. We can generate sound pressure waves in the air. We can light up a display. We can move a robot arm. We can print 3D new objects or synthesize a new kind of protein. For example, in digital audio, the transducers from air pressure to voltage variation and voltage variation back to air pressure are essentially unchanged from those in Bell's experiments. What's different now is that we sample those continuous voltages to produce a stream of numbers, which we can transmit over the network or record on a storage device for later manipulation or transduction back into sound. We can do symbolic manipulations on the stream of numbers, known as digital signal processing. We can even do away with the microphone altogether and generate the stream of numbers according to an algorithm or a universal function trained on data. or instead route a data stream gathered during an experiment through the same signal path for symbolic manipulation, storage, transmission, or digital to analog conversion to a sound pressure wave in the air. All of this is data-driven sound, but not necessarily data sonification. My favorite definition of data sonification has always been a mapping of numerically represented relations in some domain under study to relations in an acoustic domain for the purposes of interpreting, understanding, or communicating relations in the domain under study. There are two parts to the definition, a technique and an intent. That a sound is data-driven is necessary but not sufficient to call it sonification. It must also have been designed with the intent of understanding something about the way elements in the original domain are related to one another. The applications of data sonification exist in a space where the axes range from public to private, from passive to interactive, and from communication of known information to exploration and discovery of new knowledge. For example, if your intention is to put on an outreach event and to inspire a sense of awe for science by evoking what Alexandra Zuper calls an experience of the auditory sublime, you're probably operating in this red area, communicating known information to a passive public audience of non-specialists. I bet if you were to do a Google search right now for data sonification, most of the results will be in this area, citing goals like accessibility, enjoyment, inspiring people to want to know more, and evoking a strong emotional response to data. But if you're like me, you probably spend a lot more time in this solitary blue space in the bottom near left, working alone or with a couple of collaborators, interactively probing data for unknown patterns in a tight feedback loop with lots of analytical listening, false starts, more data wrangling than you expected, and multiple iterations, using sonification not as an end in itself, but as a means for discovering something previously unknown about the underlying phenomenon. For the past 5 years, I've been collaborating with Kurt Hebel and Martin Grubela on a series of projects where we're using sound to explore complex data. And our work has been mostly in that blue zone from the previous slide. A small group of collaborators interactively probing the data to discover something about the underlying phenomenon that wasn't previously known. In the course of our work, we started to realize we needed a term to describe our way of working. Most people associate sonification with public outreach, with turning data into music to tell a story that we already know. Our goal wasn't just to tell a story about something we already knew, it was to use sound as a tool to discover something we didn't know yet. So we coined the term auditory analytics to describe a method of integrating sonification and analytical listening into a larger cycle of research and discovery, using the ear to help uncover something new about the underlying phenomenon. In this context, sonification is not an isolated goal in itself. It's an integral part of a larger research cycle that includes collecting raw data, deriving data sets, designing multiple mappings of data to sound and visual representations, analytical listening, forming hypotheses, and building tools. Typically going around this loop many, many times, generating multiple different mappings, building new sonification tools, and sometimes collecting additional raw data before going around the loop again. As mathematician Richard Hamming famously wrote, the purpose of computing is insight, not numbers. And in auditory analytics, the purpose of sonification is not sound, but insight. A lot of attention is paid to techniques for mapping data to sound, but the dual of data sonification, analytical listening, is equally important to auditory analytics. The ubiquity of meaningless sound in daily life is training us to receive sound in a passive way, allowing it to wash over us without interpretation, encouraging us to relegate it to the background. Analytical listening is different. It's not just hearing, it's actively listening to an audio signal with the expectation that it carries meaningful information. Each of us has an innate capacity to interpret sounds in the natural world. Analytical listening taps into that ability, allowing us to extract information encoded in sound. In other words, analytical listening is what Stern described as the audile technique, the skill that was developed by sound telegraphers in the 19th century. It's harnessing your innate powers of auditory perception for the purpose of extracting specific information from a field of sound. So let's move now from the theory to practice with a case study involving shape-shifting molecules. While the subject is molecular dynamics, the underlying challenge is the one we all share: how to make sense of complex, high-dimensional time series data. So as you listen to the molecular dynamics examples, I hope you'll also hear some possibilities for your own research. This is work we did with members of Martin's lab at the University of Illinois to study the dynamics of how a protein changes from a disordered string of amino acids to its functional, compact, folded state. In Martin's lab, they're not just interested in the final folded shape. They're focused on the dynamics of how it gets from one conformation to another. It turns out there are multiple paths a protein could take, from the squiggly unfolded shape on the right to the more structured protein on the left, a path that Martin calls the journey. To explain the journey to his undergraduate students, Martin came up with a simplified 2D lattice model, where a protein is represented as a string of black and white beads. As in the previous slide, there are multiple pathways this simple protein can take to change from the disordered shape on the right through various intermediate shapes to the folded shape on the left. The dynamics of the simple model are described by just one rule. On each time step, one segment of the 2D molecule can bend by 90 degrees. If two beads of the same type are adjacent, they bond to each other, and each type of bond reduces the energy by a specific amount. So the folded state has the lowest energy, and the less folded shapes have higher energy. So imagine you start with a straight string of beads over on the right, bend one of the segments 90 degrees, and you end up with a new shape, and so on. I was intrigued by his slide because it reminded me of a finite state machine. So I used context-free grammar to specify the likelihood of each state transitioning to each of the other states, where transition likelihoods depend on the temperature. If you redraw the journey to put the highest energy conformations at the top and the low energy states toward the bottom, it ends up forming a funnel shape with lots of high energy conformations, fewer medium energy conformations, and only one minimum energy conformation, the folded state at the bottom. Each purple arc connects shapes that differ from one another by a single 90-degree bend. So it becomes almost like a board game, where on each step, you're allowed to make one move along one of the purple arcs. If you assign a fundamental frequency to the fully folded state at the bottom and a different harmonic of that fundamental to each of the other states, you can see and hear the paths that a protein takes over time as it moves from one shape to another. And so on. Yeah, it doesn't have an end to it. It's like real proteins. This is a different animation driven by the same grammar. The current state is shown by a yellow square on the left, and the shape of the state is shown on the right. The purple lines here show the states where it could go next. Each time you enter a state, it triggers a percussion sample unique to that state. So this example starts out stuck in a trap, which is a local minimum. And eventually it escapes, only to get stuck in another trap on the left. Eventually it does find its way to the lowest energy folded state. And like a real protein, even after it gets to the folded state, it doesn't necessarily stay there forever. It still has some likelihood of popping out of it. Martin ended up replacing his original slide with the animated sonifications for his course. But so far, this was still communication of well-known concepts, not discovering anything new. So he suggested we publish it in the Journal of Chemical Education. The models actually used in research are atom-by-atom molecular dynamics simulations. In an MD simulation, on each time step, they use Newton's laws of motion to update the position and velocity of each atom of the molecule. The resulting time series is a 3D simulation of the atomic level configuration of the system at each point during a simulated time interval. Because the positions and velocities are updated once per femtosecond, the MD simulation generates a tremendous amount of data. So to get a handle on the dynamics, researchers often use one-dimensional projections called order parameters as a kind of proxy for the size or the foldedness of the protein. For example, the one called SASA and EHA are measures of how much and what type of a protein's surface is exposed to the surrounding water molecules. Radius of gyration, or RG, is an order parameter that gives a coarse estimate for the size of the protein. It's computed as the Artemis distance of all atoms from their common center of mass. In the context of the auditory analytics cycle, computing an order parameter trajectory corresponds to the stage of deriving new datasets from the raw data. The arrow labeled f of x corresponds to mapping those data to sound in multiple ways. The most direct mapping is a one-to-one transduction, related to the continuous physical transduction Bell used for the original telephone. For example, we could take the 3 million or so data points from the RG time series and play them back as an audio signal at 48 kilohertz. What originally took 653 microseconds in the simulation now takes 68 seconds to play back as an audio signal. It's a one-to-one transduction with no decimation, so there's no loss of data. And this is what this sounds like. So when we tried this, our first impression was, oh, it's just noise. But if you go into analytical listening mode, you start to notice some structure to the noise. It sounds like a low amplitude broadband or white noise mixed with some soft crackling, interrupted by aperiodic bursts of high amplitude low pass noise. And it seems to spend more time in the soft sections than in the louder bursts. Knowing that RG is a proxy for the size of the protein, you could infer from the sound that this might be a bistable system in which the low amplitude time intervals correspond to the compact folded state when the protein's size is smaller and its movements are more constrained, and the high amplitude bursts correspond to the unfolded ensemble of states in which the protein is larger and has fewer constraints on its movements, possibly more like a random walk, which is the integral of white noise, so it sounds low-pass filtered. But we were primarily interested in the transitions between folded and unfolded states, which in the RG audio signal corresponds to the vanishingly brief time interval like this one selected in blue. In this representation, the transitions appear to be nearly instantaneous. To hear what happens during a transition requires some way of expanding the duration or zooming in. In other words, you want to be able to stretch something that takes about 10 milliseconds to something that takes more like 10 seconds. But then the rate of change in the signal is likely to fall below the range of human hearing in terms of fine structure of the waveform. But you can hear those changes as slow modulations to a faster audio rate signal. This is the idea of Bell's photophone, which used sound vibrations in the air not to generate light, but to modulate the intensity of a beam of sunlight. In a similar way, you can use a data stream to modulate the parameters of a sound synthesis model. You never listen to the data stream directly. Instead, you perceive its effect on the audio being generated. Here's a selection from just before to just after a transition in the EHA order parameter. So that lasts less than half a second. Now here's the same transition stretched 48 times longer, with the data mapped to deviations in both pitch and amplitude. This is how we first started to hear that the transitions were not instantaneous. As you heard in the direct transduction mapping, when the protein is folded, its order parameter values are small and don't vary as much. When it unfolds, those values and their fluctuations increase significantly. To capture this, we defined a 2D projection that we call mu sigma space. We took the running mean, mu, and the standard deviation, sigma, for each of the three order parameters to create a 6-dimensional dataset. Using PCA, we reduced those down to two principal components that account for 98% of the total variance. In this new space, the folded states cluster at the left, unfolded states toward the right, and the transition passage spans the space between them. When we listened to the transitions in mu sigma space, we noticed that there were several direct, fast transitions that we called highways, shown here in red, and some slower, less direct transitions shown in green that we called meanders. The lower graph is a zoomed-in view of the RG trajectory, and the upper graph is that same trajectory through mu sigma space, where folded is toward the left, unfolded toward the right, and transitions in between. A red dot shows you the current time, and I slowed down time during the transitions so that you can hear more detail. So, hearing this prompted us to ask, what makes some transitions fast and others slow and meandering? Martin had a hunch that there might be a correlation between the speed of a transition and the dynamic pattern of hydrogen bond formation during that transition. When it's in its unfolded state, most of a protein molecule's hydrogen bonds form with surrounding water. But some amino acids are hydrophobic. They act like oil and are repelled by the water. This causes the protein to fold in on itself with all its oily sections hidden in the center. The collapse allows the rest of the protein to form a stable network of hydrogen bonds directly with itself, creating a compact structure. So we decided to look at the sequence of hydrogen bond formation events during the transition between folded and unfolded. So this is an animation of the center region of the protein while it folds, with hydrogen bonds shown as dashed lines. As you watch the animation, see if you can spot any patterns in how these bonds form and break. We found it nearly impossible to track this number of spatially separated events with our eyes, in part because there are multiple bonds that you have to track and they're scattered across the visual field. On top of that, the molecule is rotating, so key bonds are sometimes hidden from view, making it incredibly difficult to detect when bonds might be changing together. But this is exactly the kind of task where the auditory system excels. The auditory system evolved in part to help us track multiple sound sources in a 360-degree environment, even under conditions of partial or total darkness. We're especially good at this when the sources are separated in time and location and occupy different frequency bands. So we tried mapping each bond event to a sonic event, a grain of sound like this, where each grain is localized in time, in pitch space, and in stereo position. We called this the polyphonic Geiger counter, but it also has a lot in common with Bell's harmonic telegraph. Now we're back at the analytical listening stage of the cycle again. But if we learned something from the 19th century telegraphers about audile technique, it's that each of us already has some innate ability to do it, and everyone gets better at it with practice. For example, listen to the direct H-bonds forming between different parts of the protein with itself, and raise your hand when you hear a dramatic change in the soundscape. So you just use your ears to identify one of the signature patterns of hydrogen bonds associated with the transition to the folded state. By interactively listening to subsets of amino acids and H-bond types, we immediately heard an association between dynamic H-bond formation patterns and how quickly or slowly a transition occurred. Then we spent a lot more time confirming what we'd heard by automating the identification algorithm and performing standard statistical analyses. Our ears told us there was something to find. We just confirmed it with modeling and statistics. And somewhat coming full circle, in the process of reverse engineering how we had identified the H-bonds patterns by ear, we arrived at an idea for a new visualization tool that we called the piano roll. In a way, it's a visualization of our analytical listening process. Interacting with the piano roll in conjunction with the H-bond sonification made it easier for us to detect cooperativity among spatially separated H-bonds as they form or break simultaneously during a transition. The visual trace gives an overview of what's coming up and what has just passed. And the sonification provides higher temporal resolution than the pixel resolution provided by the screen. Discovery requires active exploration. You need to be able to build new tools on the fly to answer questions as they come up. And ideally, sonifications and visualizations should be interactive so researchers can explore the data on their own terms. To facilitate this, we've been developing a modular framework inside Kima for concurrent sonification and visualization. This allows us to quickly prototype and test multiple different mapping strategies, which is an essential step in the auditory analytics cycle. For example, this part of the graph defines a sound generating algorithm, and it's modular, so it can be swapped with any other compatible algorithm. To specify that a sound parameter can be controlled by data, you set it to a variable. Here, the frequency of an oscillator is set to the variable log freq in units of pitch. The data mapping environment is part of the same signal flow graph. To define a mapping, you declare the target variable log freq and associate it with a block of code to execute on each row of data. This example reads a value from the endpoint column. There are several options for normalizing. Warps that value through an adjustable curve for log, linear, or exponential perceptual scaling, scales the value by pitch deviation, and offsets it by pitch space. This allows researchers to adjust the range of the values while they're listening, either to bring out aspects of the data or to place sound in a range where their own hearing is most acute. Last summer, we did a project with Martina Haveneth and her postdoc Guanlin Chen at Ruhr University in Bochum. This time we analyzed a different shape-shifting molecule, poly-N-isopropyl acrylamide, otherwise known as PNIPAM. It's a synthetic polymer known for its ability to rapidly and reversibly expand or collapse in response to a critical temperature threshold. The collapsing behavior reminded us of protein folding, so we hypothesized that PNIPAM might collapse in the same way, by forming internal H-bonds directly with itself. So we started a new auditory analytics cycle by simulating a 30-unit long PNIPAM chain surrounded by over 32,000 water molecules in a 10 nanometer cube, and then searching the resulting data for direct hydrogen bonds. We mapped those direct bonds to sound, and the result was almost nothing. There were hardly any direct bonds associated with the collapse. I mean, there are a few, but nothing like what you heard for the protein folding. So we went back to the drawing board, back to the raw data, to look for other types of hydrogen bonds that might be driving the collapse. We identified 3 types of hydrogen bond interactions we wanted to listen to. First was the direct NHO bonds that the polymer forms with itself, and we already knew those didn't tell the whole story. We also identified some unexpected NHN 90-degree interactions that we called side chain bonds, and we found a type of water-mediated bond called a water bridge, where a single water molecule bridges as many as 3 contacts along the PNIPAM chain. To make it easier to monitor PNIPAM state, we used principal component analysis to project a different set of order parameters down to a 2D state space. In this excerpt, the moving red dot is tracing one trajectory through that space. Yellow on the left is the collapsed state. Magenta on the right is the extended state, and the blue in the middle is where the molecule transitions between the two. What we're hearing are the side chain bonds for which a single donor hydrogen is interacting with more than 2 acceptor nitrogens. Like the direct bonds, the side chain bonds didn't sound strongly correlated with the compact state. This is the new and improved piano roll that made it possible for us to listen to one type of bond while seeing another type, effectively adding a 3rd or 4th dimension to the visual display. But in this example, we can listen and see the pattern of water-mediated bonds that form and break as PNIPAM collapses and then expands. So it was not the direct bonds, but the water bridges that seemed to initiate and organize PNIPAM's collapse. We could also hear that PNIPAM is not a simple two-state system. We heard evidence of some intermediate states and long-lived H-bonds that seemed to slow down some of the transitions. Well, we always like to say the ears tell the eyes where to look, followed by the rest of the brain. In auditory analytics, sonification can draw your attention to something you hadn't noticed before, inspiring further investigation. Analytical listening can lead to new hypotheses and guide the research in unanticipated directions. The same can be true for visualization. In auditory analytics, sonification is not an artifact that has meaning in isolation. Instead, it's part of a process that includes visualization, statistics, model building, verbal descriptions, mathematical descriptions, and often requires running new experiments. The parable of the blindfolded scientists and the elephant is a reminder that no single data set or sensory modality, visualization or sonification, can ever provide a complete map of a phenomenon. Instead, scientific facts are established progressively through a cascade of evidence, making observations, gathering raw data, extracting derivative data sets, mapping those data in multiple ways like sonification and visualization, analyzing those mappings to build models and verbal descriptions that are themselves analyzed to build new models and verbal descriptions, and so on. Each stage of which contributes to transforming raw data into a cohesive, cumulative argument. In auditory analytics, data sonification and analytical listening form an indispensable part of that cascade of evidence. So this is just a slide with links to some of the papers that I referenced. And I turn the stage back over to you.
Super. Thank you very much. Amazing. Thank you. There is no applause transported in Zoom, but which is our constant problem. But this was really amazing. I particularly like the end that you said, visualization, sonification.
Max, I can't hear you.
Oh, really? Okay. Let me try this again.
Is it? Can you hear me now?
Yes, yes.
Okay, I need to get rid of the feedback. So now it should work. Okay. Yeah, so yeah, there is, and let me do the following. Let me switch on my camera because otherwise nobody can see me. Okay, yes. So this was amazing. And there is, I don't know, it's really hard to put into words how much the resonance is with not only cultural data analytics, but particularly also data visualization, information visualization, and so on. While there is some very important nuts that you put into the chocolate, which are typically left out because we don't do this kind of like natural extension to sound. And with the sound, there is another thing coming in, which is sort of the natural mathematization of it. Like you sort of like naturally bring these things together, which obviously they were never apart since Helmholtz, let's say. But in the humanities, we we, you know, as a community, we strive a lot to sort of get math out the door, right? So this is sort of like, I studied art history, and it was almost sort of like a revolution to sort of like suggest that we should actually count and do frequencies and stuff like that. And I think that is a really, really amazing thing, that how naturally you bring all these things together. That your example is in chemistry should not sort of like disencourage the audience that this can only be done in these kind of areas, because of course, yes, in culture we have less data, for example, but again, we have lots of temporal data from super high frequency, such as trading information, to human mobility, to sort of like stuff where we have way less, you know, so let's say dense data, like for example, artworks in history and stuff like that. So there's a huge amount of problems, but nevertheless, there is, I think, something super inspiring about what you're producing here. And so there's a number of things which I may be familiar with, but I think our audience may be not so familiar with. And there's my first question is asking you to explain a little bit what you sort of like introduce as this modular framework in Kuma, which those of us who sort of like do some, you know, dynamic data visualization or even sonification, they may know things like Maximus P, Touch Graph Designer, Super Collider, and so on. But I think the great majority in digital humanities, and I know for a fact network science, for example, complexity science, a lot of people don't do that. They do things where they sort of run mathematical models, and they use Python, R, Julia, or C++, whatever. But it's not sort of a thing to put these sort of like modules together with an input and an output, as you have shown in this sort of like modular sequence diagrams, which look a lot like old school sort of like, you know, sort of like flowcharts from computer science. But if I'm rightly informed, in Kuma, these are actual, you know, it's basically like patching together modules in an analog synthesizer. So there's some actual action going on. And I think it would be really interesting to sort of like learn a little bit more about like how that workflows. Like imagine you have a tabular data with some timing, and then you get this thing in, and then there is your visualization coming out. So in some sense, it's sort of like asking for a sales argument for like your sort of like product, because it is in a box, it is a product, but I think the audience shouldn't understand it as a sales pitch, because certain things need to be in a box, in the same way that early knowledge graph databases were run on the connection machine because you needed this massive parallel computer to sort of like run it without latency. And I think there's a very similar thing going on, and you can probably speak to this because you have like decades of experience in it, right?
No, thanks. I don't actually think of it as, I think a better analogy than the patching of a modular synth. I think of Kima as functions, and because the function can hide details inside of it, it makes it more modular, which has always been the goal for Kima in general, that you can, no matter how complex this network gets, you can always just treat it like it's a sound. We call it sound, right? Every complex network is just called one object, could substitute for any simple module in a different graph without interference. So that's the idea behind it, is to be able to build up these pretty complex signal flow graphs and then kind of collapse them and treat them as, well, this is just the input. This is just the source. This is the source. And this other part is going to be modifying the source.
Super nice. Like, there's a question which immediately comes to like my mind, having seen a lot of computer animators doing things with Maya and stuff like that, where whenever I see a cinema movie where there's a lot of digital effects, and you know there is this sort of like function graph somewhere in the background, would it be possible to have a second IMAX screen with the full sort of like function graph of Avatar. And as I watch Avatar, I can see which function is actually active and does something.
It would be like live coding performance.
Yeah,
or
exactly.
something.
So is that sort of something that has ever interested you? Is like not only like what does your data do and like, you know, sonify and visualize that, but like actually sort of bending that whole paradigm back to your sort of like, you know, have an infinite number of oscilloscopes and spectra or whatever.
Yeah, so I kind of think for that
Mhm.
there's real time and there's everything you do to prepare for real time.
Mhm.
So I mean, so the part that you're describing, like the building up of the network, I consider that is preparing for real time. And real time is that mode you're in where there are no do-overs, right? Time is flowing by and you're making decisions on the fly, and that's your performance, that's your live performance. But then there's quite a bit of time in the blue box, maybe, where you're alone and you're trying things out and you're setting things up. So I'm not, yeah, but it's an interesting idea, and probably it would be somewhat interesting to see the inner, see like the inside, like a factory tour or something. You see, how is this sound made? That could be kind of interesting. But yeah, I've up to now just been thinking of it as like that's preparing for real time. And the real time you don't see the computer at all. You see the performer, you hear the performer.
Thank you very much. So I'm gonna give the question to Mike, and because we have the sound problem on the main thing, I'm gonna ask Mike to use his camera, his microphone, and his speaker. Thank you very much.
Okay. Can you hear me now?
Yes,
Yes, I did. Can you hear me now?
yes, I can.
Yeah, but my speaker's on. Okay. And now can you say something?
Test. Can you
Oh yeah.
hear me?
Thank you. Let me. Okay, yeah, because this weird thing of switching between
Yeah.
one sound and another. Basically, I should admit that I came here sort of being somewhat skeptical about all this sonification approach, maybe because my familiarity with it was mostly in that domain which you've shown, which is mostly demonstrational. And I can say I'm 100% convinced, but I am. You shifted me a lot, I would say, in my attitude to this thing. But nevertheless, so my qualitative feeling from the multiple examples you showed was that in majority of cases, but not in the all, in majority of cases, my personal, maybe I'm less an audile person than Max, for example, but my feeling is nevertheless I am looking at the picture and the graphs and grasp information from there, and then it is confirmed when I hear it. There are sometimes some other examples when actually sound leads. Anyway, I mean, it is clear to me that they sort of mutually reinforce, so to speak. So there is both of these things are useful, and probably there are some use cases when so can you somehow reflect on this idea when sound leads and when sort of graphical information leads, or sort of it is easier to see on a plot and when it is easier to hear?
So I agree with you that when they are functioning together, it's stronger
Mm-hmm.
than either one by itself. And I think there's, evidence that we are multimodal creatures, that we're doing some kind of a sensor fusion all the way from the lowest level of the sense organs all the way up to the central nervous system is multimodal. So
Mm-hmm.
so that I agree with you, that I've found it to be often stronger to see both. And why not? Why not use everything you can to get the
Mm-hmm.
information
Yes,
out?
absolutely.
Now, where it can be stronger or lead, there's certain situations, let's say, in a virtual reality that you're
Mm-hmm.
creating, if you want to let the person know that something happened behind them, you would
Mm-hmm.
have to use sound for that.
Yes.
And similarly, if you are attending, or like in the piano roll, the newer piano roll, we could switch between showing one type of bond and listening to a different type of bond. So that was actually adding more dimensions to the graphic. Like the sound is giving you a deeper third or fourth dimension to this 2D signal or 2D representation. So that would be another case. And the case of the hydrogen bonds, where, if you think of a natural environment, you're monitoring many, many things at the same time with sound. If you're looking at your computer, you're aware of the ventilation turning on and off, some traffic outside. And so you are monitoring lots of things in this 360-degree environment. And so in the case of the hydrogen bonds, by putting each hydrogen bond at a different frequency or a different pitch, we were able to hear coincidences and things happening together came out really strongly, where, as you saw in the picture, the normal way of the protein model, you couldn't tell what was going on. There was too much going on.
Yeah, that's probably a very good example. And
Can you switch on your mic again and your speaker? Sorry.
what I should do?
So the key thing is, like, there should be, I'm very sorry, Carla, this is like the one talk where this shouldn't happen. So whoever speaks switches on the mic and the speaker, basically.
That I'm doing now.
Okay.
Is it as one example, is it probably correct that, for example, if we are thinking in terms of principal components of some trajectory, it is very difficult to visualize more than two or at most three of them. And in terms of sound, if you put different frequencies on different principal components, then you can hear stuff.
Right.
Yeah.
Or add more components that you're not displaying, the ones that aren't displayed.
Yeah, exactly. You can hear more components than you can see. Yes. Yeah. That actually makes sense to me. Yes. Thank you.
Thanks.
So there's a whole bunch of things which sort of, like, I think are sort of supernatural in this sonification and sort of sound educated literacy crowd, while they're not so straightforward, I think, in the sort of broader humanities, cultural research, and so on crowd. And in particular, like what we're just talked about, like PCAs, you have like you break it down to something that's two-dimensional or three-dimensional, same with UMAP or T-SNE. And then what is actually sort of like the cool thing about music and sound is that we were super attuned to sort of have super complex timbre landscapes where we can differentiate like all the symphony orchestra instruments in a symphony recording, for example. But and then there's also this intuitive thing that if somebody throws something down in the kitchen in a restaurant, you probably can hear what this was. If it's made of
Right.
glass, porcelain, probably you can even hear the shape, even without training, like if this was sort of like something roundish or something flat. And
Yes.
so that is a sort of like really interesting thing. But the key thing is, how do we actually train this literacy? In visualization, this has been very hard, right? So people do scatter plots, box plots, violin plots, node link diagrams with spring embedded layouts, with whatever layouts, and so on. And that is already hard. And then people still say, oh, that's a ridiculogram as a node link diagram and whatever. And so how do we actually sort of like get out of this corner, which I have to admit for visualization and actually for all of science, like, I always have the feeling that I'm forced to sort of like leave my blue little box, which I'm sort of addicted in diving into, to go to the other corner. Like if the dean asks you to teach a visualization course, like the UT Dallas, this was the case, I called it using information visualization to think, as sort of like the contrast to information
Nice.
visualization to communicate. Obviously, you cannot sort of like go fully that way, but like the interesting point is actually to do visualization, for example, that make no sense for anybody else, because you would have to have this literacy trained in order to hear certain things. And what you're doing, like, not everybody on Earth needs to hear what a certain hydrogen bond, or sort of like, what was the word? This sort of like water bridges or whatever. Like, not everybody on Earth needs to differentiate that. But obviously, whoever is the biochemist working on the molecule that you're supposed to take when you have cancer, for example, these 15 people on Earth should probably really have their act together in doing this. So do you think there is a sort of like structured and principled way of learning this, in the same way people may say learn an instrument to do classical music or something?
So I'll answer the unstructured, unprincipled way first, which maybe if you set the visualization or the sonification up in such a way that it's interactive and the researcher can kind of poke around, change things, rotate. I
Yeah.
think very quickly you teach yourself. You teach yourself a meaning, especially if you are motivated by wanting to know something, like you really want to get that information out, then you're motivated also. But so we were working with biophysicists and and physical chemists, and they learned it. I mean, they did so. They didn't have to go through a rigorous ear training course necessarily. They tried it a few times. They got the idea. They were familiar with the underlying phenomenon, so they got it pretty quickly. And I think it's because it was interactive. But the like principled way, I think, probably has to go back to kindergarten. Because I think that all of us have been trained since kindergarten age on line graphs and visual literacy. I think it starts very young in the school to learn, verbal literacy, reading literacy, and visual literacy are taught at a very early age. So I think ultimately that sound literacy should sneak in there too. And then it will become more natural. And I actually think that as scientists, as everybody gets more trained on sonification and animation, that there will be some new discoveries. I think new science is going to come out of things that are time dependent. Because so much of the kind of classic training that you get in school is, there's a flat page or there's a flat screen and you have a two-dimensional picture that's static. And so, but phenomena really aren't that way, right? They are dynamic. So I think we're going to be finding new science because of giving people a way to perceptualize dynamics.
I think you have I fully agree. This is sort of like, people are trained informally, for example, by playing computer games in which certain events are sort of like associated with certain triggers and spawning of whatever, of particles which have a granular sound attached and whatever. There's one interesting thing, which is, and this is going back to sort of like your idea of sort of like a finite state machine, that in computer games this is actually true. In the real world, it is not. The amount of sort of like intricate configurations and constellations of the world, particularly in the continuous medium in which we operate, which is, you could imagine the fluid of culture or whatever. You even if it was discrete, you would have way more possibilities than there is atoms in the universe in terms of visual pictures possible, in terms of sound possible, and so on. So one of the key, like, if you want to make snarky joke in relation to physics, it was like the world is not a bunch of hexaflexicons with like states, right? So the question is, can we how do we deal with that? Is sonification sort of giving an advantage dealing with this sort of like world that cannot be fully permutated against all states? And do we get a better feeling for it? And is that something we should actually do? Sort of like, for example, what I found very convincing this last better piano roll, where you had sort of like your PCA, and then you had this like massive set of things where you could totally, by listening to it once, you could tell like, oh, if I could repeat that, I would like to listen to this like 20 times. You probably get a feeling for what's actually happening in addition to these sort of like two principal components, like the not so principal components in a sense, right?
Yeah. And I didn't demonstrate that, but yes, you can control time through it. You could just stop it and jump to different spots and just scrub over a small amount of time. So, yeah.
So is that something where you would say there is a sort of like playing with the knobs, so to speak, walking into like around in the space, turning certain things up, where it's a little bit like you put your hand on different objects in the room and see how they vibrate with whatever the environment gives you. Like, in an airplane, you can do that. Like, where can you feel sort of like the turbulence more or less and stuff like that. So is that sort of something which how do we systemize this? Like, I think in visualization we're so inundated with these sort of conventions now. There's like, so every programming language, every school of sort of like visualization, of graphic design, of application has these catalogs of how different things can be visualized from scatter plot, heat map, and so on. But what fascinates me privately in my blue little corner, both in visualization and in sound, is actually this playfulness. It's a little bit like backcountry skiing, which these three things I think are the thing I'm most enthusiastic about. But I have the feeling that it's really hard to sort of like translate to something where we can sit in class and say, oh, in order to take arbitrary data and actually do a sonification, here is a catalog of things you want to try out. So how long do you think are we apart from this for a more broader audience? And at the same time, how long has this already happened? Because I have the feeling by talking with people from the sound and music area that a lot of things that happen right now in machine learning and in visualization often happened decades ago in sound, because it seems like they're just constantly decades ahead. So that's sort of like a paradoxon, isn't it? Like at the same time, visualization is more sort of conventionalized, while at the same time, sound had this head start. And so how do we deal with this? I find this a super crazy conundrum.
So you're wondering if there could be Python, you just have like a list of things that you could try with the sound.
Mhm.
Is that, yeah?
Yeah,
Is
yeah.
that where you're headed with that? Because the way I've tried to approach that is that at least in Kima, the way I approach it is that I've got some, so I should have showed the screen, but anyway, you can open up like a spreadsheet kind of data
Mhm.
display, and then there's a gallery, so you can try different things, and those are already pre-made. So you can do a sonic histogram, or you
Mhm.
can do just map the values in this column, use those as start times, and use the
Mhm.
values in this column as the change in pitch, things like that. But
Mhm.
there's a gallery that's kind of pre-made to do those a few standard things, and then I guess they're standard. They're not standard, but they're just there's a gallery of possibilities. You can try them, and then you can go in and modify it and alter it to be
Mhm.
what you need. But maybe you don't need it, right? So you could just play with it for a while and listen and look and decide if you want to
And
go
would you think
further.
there is a sort of like frequency distribution that people always do the same thing, like map pitch to some kind of amplitude of frequency? And is it,
Maybe.
or
I
is
mean,
there?
pitch. We're extraordinarily acute at discerning differences in pitch, right?
Mhm.
So that's a very strong one to use if you want. And pitch with respect to time, right? We're really good at hearing fine changes in that. Or hearing two different streams, you can really tell when they deviate from one another, right? They sound the same, and then you'll hear beats, and then you'll hear them like two separate things, and
Mhm.
so yeah. So yeah,
Which brings me
Joseph.
back to the multiplexing thing that you mentioned,
Yeah.
which I find super fascinating. Like I do this with visual, like with color, for example, which is cool if the people you work with can see, for example, the constituents of RGB or CMYK. Like there's some people who can do that. I can say
Oh,
this
okay.
color is
Yeah.
made out of these three sort of components, and then you can actually compare three different sort of sets of data. I've never used this in a publication because I just assume the broader audience, just doesn't.
But you can do that. Can you see a part? You can
Yeah,
see the
yeah, but
components.
this is
Oh,
sort of
that's
like
cool.
I think there's, with like anybody who's worked in a print shop often can, right? But there's like that's probably a very, very, very niche in your little blue cube, right? So the question is there ways to sort of like do this more? Is there ways to multiplex which are sort of like more natural in sound because everybody sort of knows how to do this. Like, we know when two people sing out of tune, trying to hit the same note, but is there some more intuitive multiplexing ways in your experience?
Well, I think if you are able to make them independent of one another, like so they're not in the same critical bands, let's say in the hearing, then that makes it easier. If you let's say that you pick, it's related to when Bell tried to use the switching on and off, and
Mhm.
he said, "Oh, well, the line became saturated." And I think it is because it was generating an infinite number of harmonics. And so they weren't independent of one another anymore. So let's say if you picked, instead, let's say one experiment, you took sine waves and they were at harmonic frequencies, or they were harmonics of each other, of the fundamental, then that would make it quite easy for someone to hear that they're separate and track them separately. And then if instead you put samples of a drum and a sample of an electric guitar and a sample of a voice, then the harmonics of those samples would be overlapping with the fundamental of the other components. So you've made it more muddy then. Is that what you're asking about, how you can make it, if you can constrain it to be in its own space,
Yeah.
in the spectrum and its own space in the stereo or quadraphonic field and
Yeah,
its own space in time, then you're making it more easy to pull them apart.
maybe the comparison is we did this video where people move from their birth to their death location, and it's sort of like it's a scatter plot where then there's an arc whenever somebody completes the journey. And the intuitive thing about this is it looks like in the back of an airplane, in the airline magazine, you always see the arcs where the airline is going. So nobody needed an introduction to the kind of visualization, because like you basically say, here we move from birth to death, and the rest is just your airline magazine, basically animated. And so that is sort of something which I think is sort of where sound has the potential to sort of like harness things which people do. They don't think about it, but they're insanely skilled in doing so. In the same way, everybody's insanely skilled in like recognizing similar images, right? Like if nobody, like if there's a poodle that has the haircut of a lion, you're not scared. Everybody sees it's a dog and it's tiny and cute. So that is sort of something which I think in sound, there's a lot of these things where we're sort of way more attuned to, in the true sense of the word, and way more capable as humans, even though nobody told us so. And we just have to switch to that sort of like conscious mode, isn't it?
And part of it's just the expectation that there is something meaningful to get. Because as I said, I mean, I really believe that we're being trained not to listen, because you go, let's say you go to a club and you can't talk to someone, you end up yelling at each other. And well, shouldn't you be listening to the music? No, because you're yelling to each other. Should you listen to the person? You can't hear the person. So, there's just lots of unnecessary noise, like fans and different traffic noise that there's like very little attempt to control that noise. So there's just we don't expect the sound to mean something. We expect speech. I mean, if you hear someone speaking, you expect that you're going to get some meaning from it. But for the non-speech audio, often even music, sadly, by playing the music all the time, everywhere you go, well, I guess especially in the US, it's that way. It's very bad. So it's sort of telling you, just, this is just background, don't pay attention. So the first step or a big step is just to pay attention, say, okay, I know there's meaning in here, so I'm going to pay attention to it. No.
No. I fully agree. I was just thinking about this example of Mariah Carey's "All I Want for Christmas Is You," which everybody hears all the time, and nobody ever sort of like puts on a vinyl record with really good speakers that actually listens to what's happened. And still very interesting, but nobody does that effort. So there's one thing, two aspects which I still would like to get into, which is one is this blue corner versus the upper right communication corner, which reminds a lot of, and so these two questions are not, like this one question will be actually a twofold thing going into the other area, which is not serious auditory analysis, but doing music. So one of the weird things about this corner is that electronic musicians very early, and not only electronic, but like people who sort of like did more experimental music, maybe with classical means, like Edgar Varese said, like, you have to have this desert, right? And so the question is there a relation between these two things? Is there between doing science in a cubicle, the blue cubicle, and this sort of like exploring what music you can do in this sort of like desert corner? Is that related? Is this the same process? Is this something you sometimes decide, oh, I'm gonna do auditory analytics, or today I'm gonna do music, and actually this is the same process, it just sometimes happens to be science and sometimes it happens to be music?
Well, that's very interesting. Um, that's interesting because it's in many ways it does feel the same, right? There's
Mhm.
this and often at the beginning not a very good feeling, right? Because there's this feeling of I'm I don't know what I'm looking for in either case, right? I don't know, and I don't even know if there is something to find. Even if I do put in the time, maybe there's nothing there. For both cases, right? Maybe I'll,
Mhm.
uh, but it does seem that there's a Uri Alon. Do you know the scientist Uri Alon? He's got
Yes.
this, a great way to describe it is that he calls being in the cloud, not not like the cloud of the data centers, but the cloud of like I don't have any orientation right now. I'm in this mist. I can't see where I'm going. And if you are, the thing is, he says you should celebrate being there because that means you're going somewhere new, right? If you knew, if you could see all the directions and it was very well plotted out, you're doing something that's been done before. There's already a path. Uh, so, so the blue zone maybe is actually being in that is in the when you're in the uncharted or or surrounded by mist and you don't know or by fog, so you don't know where you don't know for sure uh, if there even is a way out. And he says the solution is to play the yes and game, the improvisation game. So get with a colleague or something and just start brainstorming. Um, Anything someone says, no matter how absurd it is, you say yes and you take it even further, and yes and you go further and further and further. And I like to think of it as almost like roll in some way rolling the dice. Like, okay, I'm not sure where I'm going, so I'm just going to take a step, and then I'm going to take
Mhm.
another step, and pretty often suddenly you do get to see where you're going um, and find your path out. And it is a new path because you were in this uncharted area. It is a similar thing, right? Where you don't know if there is anything in the data. Like,
Yeah, yeah, exactly. So I love that you brought up Urialon. So I have like for my cultural data analysis classes and visualization classes, I have seven sort of like required readings. Three of them are one pagers, two of them are three pages, and they're both by Urialon, and this is one of
oh,
them.
okay.
And then the only one that is sort of longer is Jacques Bertrand's Matrix Theory of Graphics, 14-page summary, which is more a cartoon to stare at, basically. And so one of the interesting things about this, indeed, is that the cloud of uncertainty, obviously, if you want to do something new, you have to get in there. Like, even though it gives you
Yeah.
depression, because if you already know what you want to do, like building a bridge, going from A to B, you will never do something new. But
Right.
there is one thing which I think is the advantage of Urialan being a systems biologist, you doing auditory analytics, and us doing cultural data analytics, which is that we're dealing with complexity. So we sort of can be sort of sure there is some there. Like it's not like that we're embarked into sort of like exploring something that doesn't have structure. And I think there, like one of the most interesting sort of like sort of assurances in some sense I got there's a radio interview by Max Planck where he talks about the difference between scientists and religious people, where he says like religious people assume their religion is true and God structured the world according to how they imagine, and so everybody else needs to sort of like get lost. While in science you take the risk that you look at the world and there may be no structure. If you're very lucky, there's God at the end, but we don't know. But so he also says the world has never disappointed us. So if you take that stance and actually look at the world, there is always structure we find. And in complexity, when you have lots of little things, lots of molecules, for example, lots of humans doing something on a square, lots of painters doing a lot of paintings, you get these sort of like aggregate structures where new quality emerges out of this sort of like large amounts of sort of like local activity. So that was what sort of like makes this analysis effort so worthwhile. Now, one interesting thing which I found quite surprising, which is rare in cultural data analytics, where like if you look at the evolution of painting, the most fancy pattern you get is the arc of Piet Mondrian going from sort of like being natural to abstraction, while for all other artists is a more messy affair, or they just like stick around in one area. So in your system, you actually found something like these two attractors. So there's like some sort of something that look like this, and then there is some other area where there's sort of like these, it's almost like the molecule does aerobatics in a sense, and then there's transition in between. So that is a rather interesting thing, because that is something how anybody of us who has sort of like read enough of complexity science may think there is a sort of the state space of complex systems may actually have these kind of attractors. And then the key question is, how do they look like? And here, you showed us that we can hear way more than we could probably see, which obviously, Binod Mandelbrot said the same, all financial time series look the same, and they all sound different, and so on. And so that, I think, is a really strong case for sonification. But the question is then, how do we actually deal with this when we see something like that? How do we then go to sort of like not fall back to, whatever is the thing we can see the most, like, oh, there is two sort of dumplings of sort of things going on, so two clusters and a transition, or mathematically speaking, oh, that's a sort of like Levy flight of whatever, like if jump size distribution, and then you do the same mathematical model that people have done for 100 years. How can we get to sort of like a more accurate way to describe the world? Like, how do you go from what you hear to a new, for example, mathematical model? Like, is there a principled way, or is it just luck to work with the right mathematician, basically?
Well, I can tell you something that I tried, that I actually cut from my talk. This cut for time, like that, which was, and this is just anecdotal, but I tried a different kind of noise to model. So you heard the first RG direct transduction, and it sounded like noise. Okay. So then I wanted to try to model the noise, and I picked this thing that's called random telegraph noise, just to be part of the theme. And it's pretty remarkable. Like, I did the one, I tried this model of this two different time scales and two different amplitudes, and added them together, and it sounds very much like that RG signal. So I was asking myself why. Well, the random telegraph noise is a model of a two-state system where there's an energy barrier to overcome to move from one to the other. So there's one barrier to go from low to high, and a different barrier to go from high to low. And that's, even though that's like super simplified model, it sounded quite a bit like the RG. And I could play that for you if you want, but I would have to reshare the screen. Yes, serious?
Yes.
Oh, okay. Try to find it. Okay.
Okay.
Okay. So yeah, the idea that the protein has this energy landscape where when it's unfolded, it's in this kind of a shallow well of energy. And then there's lots of bumps because there's like these little micro states, and that it has little micro energy barriers that it has to overcome. And it has to overcome that barrier before it can go down to the folded state. So that's the idea of this thing called random telegraph noise, which is two states, and you can adjust the barrier that you have to overcome to go from one to the other. So, and you can set them to different probabilities. So you could, if you make it more probable to switch from low to high than from high to low, then you can make it a little bit more like that, like the protein, where it's spending more time in the folded state. So that was just a demonstration of it. Oh yeah. So why is it called random telegraph noise? If you take that noise and you use it as the amplitude of an oscillator, and I mean, I think any resemblance is purely coincidental, but unless you can come up with maybe a theory of communication in terms of overcoming these free energy barriers. I don't know why it sounds, does it to you anyway? To me, it's uncanny how much like the telegraph it sounds. Okay, so then, so I used a slow timescale RTN to model the loud bursts, and then layered in a faster, lower amplitude RTN to capture the crackling sound of the protein overcoming these little tiny micro barriers. So, yeah, I don't know. You were asking is how can you get to the model? That isn't like a systematic way to get to the model, but maybe that is the way to get a handle on things. Is we have to build models. Like we know something about the system, and in a way you say, well, my hypothesis is that there's these energy barriers that have to be overcome. So I'm going to model it, even though that was simple. That telegraph noise is very simple. It was uncanny to me how close it was getting to the sound of the protein's radius of gyration. So maybe by making a model and generating data, and then comparing the generated data to the data that you've actually collected, maybe that's some way of trying to come closer to your model, to what you're seeing.
Yeah, I think this is sort of like we probably don't find a solution, but I think there's a really, really interesting sort of like paradigm that we sort of like can carve out here, which is also very, very frequent in any field in the humanities that tries to go quantitative. Like if you like, I'm a trained art historian and I have this disease that I date everything. Like, I walk past the house and then like, I have a friend with whom this works really well. And then he's like, oh, do you remember this like red palace? And what do you think? And he says like 1873, and I say 1885. And then we walk back to check, and it was 1887. It's a success. I get the beer, not he gets the beer, and vice versa. We do, like, obviously it works both directions. But the question is, why is that? Like, in this case, it's sort of like spotting family resemblance and stuff like that, which in your case, there's something very similar going on. But from that sort of thing that actually works, like where you can say, oh, I have a function in my head that takes visual information, knowing a little bit of metadata, like this is architecture, we're in Rome or whatever, and translating it into a 4-digit number. That is sort of something which which sort of like there should be some kind of like mathematical function with which one can model this. Now we can do it with machine learning, which is just you have enough examples so you can even recognize cats in like weird body positions as a cat, but it's still, I think the jury is still out, like how do we do this systematically of what that kind of like sort of like formalization of a mathematical model actually can be. And that is not clear, but I think for me, this sort of like reinforces sort of something which in astronomy, for example, is a known thing, where like Fritz Zwicky mapped the sky preceding other people doing models. Like we count just how many stars that look like this, how many stars that look like this, how much gas clouds are like this. And so in the same way in art history, quantification does not necessarily mean that you need to have a mathematical model of the generating mechanisms, but we should actually systematically take a look at the stuff and actually do this cartography of what is out there, what kind of personal relationships are out there. Is it cliquish? Is it star-like, how people sort of interact with artworks? Do artworks in the National Gallery arrive there via brokers, or are they coming in a myriad of different ways? That's stuff we can quantify, even though we do not know the generating mechanism. And there's very, very similar to your listening paradigm, where you say, oh, it's like I listen to this thing from different ways, and then maybe I can understand the system better. And in some sense, do I understand you right, that there is also sort of like, you would agree that it's not just like listening so we can actually get to this one model, but also listening in a way to see the whole variety the system can take, which I think your water bridges are a perfect example, right? You found something that we just didn't know. That's like dark energy or neutron stars for Fritz Zwicky. You saw something that other people, they didn't see because they didn't model it. They didn't take it into account, that they did not sort of like look at that, because the information source came from something very different, which is this kind of like arrangement of sound.
I mean, I do like the alternating between looking at collected data and then at some point trying to generate it, right? I think I could generate this data with either because, and then you think you're going to do it, and then often you do something very simplistic, and I guess I didn't really understand. I'm thinking more in terms of sound. I think I can make that with adding 3 oscillators together, and modulating the amplitude by a low amplitude noise, or so. So you think you could do it. It's instructive when you actually try to actually synthesize something. And you do learn. I think you learn more about it as you try to model it. I think it teaches you a lot.
And you work with these biochemists who want to end up with some kind of like differential equation model of the protein folding or something like that, right? And if you're thinking of synthesis as a bunch of oscillators you patch together in a certain way and modulate in a certain way, which is also dealing with differential equations, but not necessarily writing down the differential equation. So how much do you think does this, like, how much mathematical intuition and how much, in some sense, musical intuition and sort of like knowing the instrument is part of your things? Like, do you think that this playful way of sort of like dealing with like oscillators is alternative to the mathematical intuition that somebody who just writes differential equation would have, or is it complementary, or is it actually sort of getting to the same goal?
Well, I think that intuition is rational thinking that you learned so long ago that you don't remember learning it. It's a logical way of thinking that you don't remember learning because maybe you were a little kid when you learned it. So, and I know people who have what seems to me to be a mathematical intuition, where they'll say, like, yeah, I know that this theorem is true, let's say, but I don't know how to prove it. So, but they got a gut feeling that it's true. and this, like, yeah, like we might have gut feelings about different things that we've, maybe I have a gut feeling about how to make something sound a certain way. And at some point it is because you learned it, probably by interacting again. Yeah, but the intuition, it's not magical. It's just something that you learned so long ago that you've forgotten that you ever didn't know it.
Yeah. And then there is one final question I have, a topic we haven't talked about yet, which is you snarkily mentioned modulation is the message. And so there's one interesting thing, like in media studies, which is sort of like I'm embedded in the Baltic Film Media and Art School, where as an art historian, I'm a little dealing with too old stuff. Most people do media studies. And one of the interesting things in media studies is that there is a higher propensity to sort of root yourself in Marshall McLuhan than to root yourself in the theory of communication by Shannon and Weaver, which is quite interesting because Marshall McLuhan sort of like shades Shannon by misspelling him and not putting it into the bibliography and stuff like that. While at the same time, he's famous for the sentence, the medium is the message, which I sort of can prove it, but I'm pretty sure he means sort of like the medium little box in figure 1 of the theory of communication, because it makes perfect sense. That is not the thing you send through the system, but actually the medium in the middle that you want to find out something about. So if you say modulation is the message, so let me package this in a neat little question. Like, how much do you think the work you're doing is path dependent on mathematical theory of communication, signal processing, and all that, while at the same time it also is interested and sort of intertwined with media theory, with, according to Marshall McLuhan, sort of he sort of shaded mathematization. But what you're doing synthesis with an analysis with a computer, there is no way around it. Like, mathematization is always there. So can we remarry these two positions in a sense to make sense and just, call Marshall McLuhan an old dude maybe?
But I think it is that we are all playing in the same sandbox. I mean, the things we're working with are the same. I mean, there have been methods for analyzing, let's say, in signal processing. You brought up earlier that in the audio signal processing, you could think of certain kinds of filter structures are very close to neural networks, right? So we're playing, and I think it is in part because of sharing the computer that we are all working with similar structures and processes, and there is a lot of crossover. I don't know if that's what you're talking about, but I think we're working with the same. You said that electronic music is mathematics, maybe just done in a different way or without knowing the mathematics, but still having this intuition about it. And then, I mean, I've witnessed people just kind of realizing, saying, "Oh, I'm no good at math. I'm no good at math." But then they're doing, when you put it in terms of electronic music, they do know. I'm not sure how to say it. They know more than they think they know, but it's just in a different form. So maybe it's more like the information is independent of the material or physical manifestation of it. So we've got these structures and processes. Some people are more comfortable realizing it in words. Some people are more comfortable describing it as an equation. Other people more comfortable manifesting as a sound. Other people as a visual. So, but maybe the information is often the same, or I don't want to say information as a static thing, because I still wedded to this idea of dynamics. So it's information, it's like a signal, right? The signal maybe is separate from the physical realization of that information.
Very, very interesting. I think this is actually a good sort of moment in a sense to conclude, because we're ending up in a similar position as at the end of your talk. What I find quite fascinating is that you think that it's the computer that we share. Well, for example, Cassirer and Leibniz would probably say it's the relational structure we share, which is like what allowed us to build the computer. So that is, I think, one of the key questions like I struggle with since a couple of years is like I did my PhD in art history, looking at monument documentation as a complex network, which has as a data set something that was produced by the Warburg and Cassirer circle, who actually sort of came up with this relational way to look at art history. So can I do network science because the people collected it as a network, or can I do network science because it actually is a network? I think that is a sort of like really, really big issue. So the key question is, are we dealing with the same thing because we all use the same computer, or are we dealing with the same things and the computer is just a good way to deal with it? So that is sort of, I think, something which probably may not be solved in our lifetime, and that is actually a cool thing because it probably creates enough suspense to do even more science or more music or more painting.
That is a good conclusion.
Thank you very much. This was super exciting. We have 2 Open Lab seminars coming up this semester. There's none next Monday. The next one is in 2 weeks, and then one in 3 weeks. And then the semester is already over, which is crazy how fast this goes. And I encourage everybody to check out the literature you've learned by Carla Scaletti. Check out Kuma. And also, that book, which led to this invitation, which is Pink Noises. Thank you very much.
Thank you. I really enjoyed the interaction and the topic. Thank you.
Yeah, thank you so much. Thank you. It was very interesting.
Thank you, Michael.
Thank you.